Okay, in this video, we're going to go over the following question. What are the perimeter lengths of each of the similar triangles in this figure below? And we're going to do that by using the geometric mean. Now, you remember that in a right triangle, there are a number of ways to solve for the lengths of the sides of a right triangle. One of them, the most common one, is what's called the Pythagorean theorem, where you take this side plus this side, the two sides that flank the 90-degree angle, and they would be equal to the square of the hypotenuse, which is this long side, or the side opposite the 90-degree angle. Except that the problem is that a lot of times we don't have the information to solve for each of the sides. Like, for example, on this side, we don't know what this side is. We don't know what this side is, and we only know part of the hypotenuse, and that's this little section right here, too. So we can use something called the geometric mean to solve for that. And the geometric mean uses the following concept. It takes a line, it's called an altitude or a height, which is a line that's drawn from the 90-degree angle of a right triangle and forms a perpendicular with the hypotenuse. And you form basically 1, 2, 3 similar triangles. And all the sides are, and remember that similar means that basically all the sides are proportional to one another, which each of the different triangles. So in this particular case, we're going to use a geometric mean to solve for these lengths, the missing lengths. Now let's go ahead and start just naming these lengths. Let's just call this side A, and let's call this side, actually, let me just use a different color here just to break it out differently. So we'll call this side A, let's call this side B, let's call this little section here C. Okay, and I think that we've covered each of the sections now. Now, whenever I start using the geometric mean, I always write out what the three triangles are and label them accordingly. And the reason I do that is so that I can see the lengths of the sides more carefully, more easily. So ABC, this is the large triangle. And what I know is that this long length is B. This length here, we called A. And this hypotenuse, it's C plus 2, okay? So I'm just going to write it out like that. Now, the next triangle that we can see of the similar triangles is this second largest one, which is right here. So again, let's just draw a right triangle, just like this one's a right triangle. And let's go ahead and label the sides. Now, where the 90-degree angle is, it looks like we called it D, so let's do that. If I go up the short leg, it would be B here. If I go down the hypotenuse, this side would be A. Okay? And let's see what the lengths are. So from D to B, looks like the length is 4. From B to A, looks like we called that side B. And from A to D, looks like we called that side C. All right, let's draw one more triangle, which is this little guy right down here. Okay, there's the right triangle. Where the right triangle is, or the right angle rather, is called D, so we got that. If we go down the short length, that would be C. If we go down the hypotenuse, it would be B. Labeling each one of those again. Between B and D, looks like the length was 4. Between D and C, the length was 2. And between B and C, the length was A. Okay, now let's go ahead and start using those proportions or the geometric mean to solve for these missing parts. Let's just choose a letter. Let's just start with A. Now to find A, I need to use proportions. Well, actually, let me see. Oh, you know what I can do? If I look at this one, I can actually use the Pythagorean theorem here, can't I? I can go a squared plus b squared is equal to c squared, or this side plus this side squared. This side squared and this side squared is equal to this side squared. So I could do that. But if I want to stick with the geometric mean, let's just find a anyway. So finding a, I want to be able to use the different sides that we have. So this side has a, this triangle has a, this triangle has a. So I could say, I only want to use one of the variables. So let's see, how could I do this? I could say, oh, I've got it. 4 is to 2 as b is to a. That way we'll find b, okay? We can do that. So 4 is to 2 as b is to a. No, excuse me, can't do that one because that would give me two variables. I'm going to use this one and this one. 4 is to 2 as c is to 4. There we go. Now we've got something we can work with. 4 is to 2 as c is to 4. And it works because we can just do cross products. 4 times 4 is 16. 2 times c is 2c. Solve for c. I get 8 is equal to c. So now I can go ahead and put c as 8 right there. Okay, so I've found one of the parts. And I need to change that because we're not finding A anymore. We found C. Good, now that I've got C, let's see what else we can find. It looks like I could also, now that I know that C is 8, I can make this equal to 10. 8 plus 2 is equal to 10. We know that this C is 8. And it looks like we've got everything else taken care of here, okay? Now let's try to find another side. Let's go with, let's try to find B, okay? So I've got a B here and a B here. So I'm going to say find B. And I can say B is to 10 as 8 is to B. So again, this side is to the hypotenuse as this side is the hypotenuse. So B is to 10 as 8 is to B. Again, cross products. And I get B squared is equal to 80. And take the square root of both sides. Let me just make this a little bit bigger so you can see it. Gives me B is equal to radical 80. Now again, we can go ahead and break down radical 80. Okay, let's just see if we can do that. Because it's actually, I can find perfect squares in here. Let me see, 16 times 5, I think, right? That would be equal to radical 80. Square root of 16 is 4. So now I can go back up here and label wherever I see B, I can put in 4 radical 5. Now it looks like the only letter I need to find still is A. Okay, so let's do that. To find A, again, I can just pretty much use any of these now. I can say A is to 10 as 2 is to A. So short leg hypotenuse as short leg is to hypotenuse. Solve for A. Cross products. Square root of both sides. A is equal to radical 20. Perfect square in here is 4, so this will be radical 4 times radical 5. That gives me A is equal to 2 radical 5. And again, let's just go ahead and put them into the right spots. And 2 radical 5. Now the question actually, though, remember, is what are the perimeter lengths of each of the triangles in this figure? So I'm going to have to do some more work still, okay? So this set of calculations was just basically finding the B, C, and the A. Now what I want to do is I want to find the perimeter of each of these triangles. And again, keep your work kind of organized, okay? It's much easier to follow that way. So let's start with the first triangle, triangle ABC, the big one. So triangle ABC, the perimeter again is each of the lengths added together. So 4 radical 5 plus 2 radical 5 plus 10 radical 5. And oh, did I say 10 radical 5? Just plus 10. Now remember that when you're adding radicals, let's make this a little bit bigger. Whenever you're adding radicals, remember you can only add the radicals that have the same square root, right? And then you just add the coefficients in the front. So in this case, it's going to be 4 radical 5 plus 2 radical 5 gives me 6 radical 5s. And plus 10, leave it alone just the way it is. All right, so this first large triangle, its perimeter is equal to 6 radical 5 plus 10. Now let's find the second triangle, which is triangle ADB. Okay, so triangle ADB is equal to 4 plus 8 plus 4 radical 5. That's a simple one. It's going to be 4 radical 5 plus 12 is the perimeter of the second triangle. And finally, let's just do this one, BDC. Triangle BDC is equal to 4 plus 2 plus 2 radical 5. Add like terms again, and you get 6 plus 2 radical 5. And there is how you would find the perimeter lengths of each of the similar triangles in this large triangle above. Okay, hope that was helpful.